Welcome to part 2 of this series. If you remember from the last video, this video is actually going to be about building the temperature sensor portion out of the project. First, I need to go ahead and build out our project directory structure a little more so that we can store header and source files in an organized manner. This layer diagram is going to give you an idea of what I'm kind of shooting for here. Top level here is any applications that we might create. Those applications will interact directly with our services, which are typically interface functions that will allow the application to do things like get data from a sensor, for example. The services, those are going to interact directly with drivers, and the drivers will interact with the hardware. Things are always going to go in this order. Meaning the applications will never interact directly with the drivers. The applications have to go through the services to do so. So what applications and services are we going to create? Well, the main application in our case will be the CAN bus data application. We'll call it CDA for short. The CDA is going to retrieve data from the temperature sensor, the temperature sensor service, and we're going to call it TSS for short. And then drivers are already done for us, and I didn't feel like listing those out. But let's go ahead and build those directories real quick. We'll create an applications directory and a services directory. Inside the services directory, we're going to create another directory to store TSS service. Inside the TSS service, we need another directory called Zephyr, and in that we need a file called module.yaml. We can talk about that later, but back in the TSS directory here, we need to make a CMake list.txt file. A source file and a header file. We'll create the other service folder in another video, as well as the CDA application. Okay, first things first, we need a top-level CMake list.txt file, as well as a proj.conf file. Now, proj.conf, what is it? It's a configuration file that defines the application's build time configuration settings. So if we want to use a specific feature of our board like GPIO or SPI communication, we actually need to state that in our proj.conf file. If we go and we write the code, it'll build, utilizing SPI drivers and whatnot, but it won't actually do anything unless we come in here and specifically say we want to enable it. So let's start by enabling some features that we'll need for our TSS service and some others that we'll need globally across all modules. We can always add more later. First one I'm going to enable here is logging. Zephyr has a pretty streamlined way of logging data to the terminal, and that's through their logging library. So to do that, let's type config_log equals y, and that's it. Next, our service is going to need to use SPI communication. So let's enable SPI by doing config SPI is equal to y. And if I'm remembering correctly, SPI needs access to the GPIOs, so let's enable the GPIOs. Config_GPIO is equal to y. Again, we'll add more later as we need to. All right, now we need to talk about CMake. If you don't know what CMake is, it's a build system generator that helps manage the build process of our project. So you can just think of it like a recipe on how to turn your code into a working program. And I'm going to be honest with you guys, I'm extremely new to CMake. I'm not good with it. So if you guys see or hear anything dumb that I'm doing, speak up in the comments and let me know. But let's go ahead and start building out our top level CMake file. Every top level CMake file needs to have this command, CMake minimum required, and then the version. For this project, the version you have here isn't terribly important as long as it's less than or equal to the current version that you currently have installed. Now let's go ahead and write some comments here for better organization. We'll just put our applications we add under here, hash applications, and then we'll put our services under here. Since we're specifically going to work on the TSS service, let's go ahead and add that with this command, list, open brackets, append, Zephyr underscore extra underscore modules, $, curly braces, CMake underscore current underscore list underscore dir, and then the path to the TSS directory, services slash TSS temperature sensor service. Okay, let's talk about what this line of code does, because if you're anything like me, you're like, what does this mean? I'm with you, brothers and sisters. So the list command allows us to interact with or modify a list. The list that we're modifying is the variable called Zephyr extra modules. The action that we're implementing on the list is the append here, and we're adding to that list. Now the $, CMake current list dir is a special variable that gets the directory path of the current CMake file being processed. So this variable will be replaced with the current directory this file is in. And then we have the rest of the path to our TSS service. So to wrap up explaining this line of code, any time that we create a new module, such as an application or a service, we'll need to add it to the Zephyr extra modules variable so that the build system will actually know those modules exist. Moving on, let's create a section for general stuff with hash general. And the first line of code is going to be include directories, CMake current list dir slash general. What am I using this command for? I'm using it as a way to essentially create a global header file or files that can be easily included within any other header or source file from within the project. We won't have to do any other fancy CMake commands in other modules to utilize it, because we're just going to put basic includes and macros in there, like include standard int or something. And I did forget to create that directory here, so let me do that real quick. Put in a general includes header file. Okay, next is find underscore packages. Zephyr required hints. env Zephyr base. So this line of code tells the build system that Zephyr is required. And if it isn't found, it won't build. The hints keyword tells the build system where it's located, And so far I've seen it's pretty typical to use the environment variable Zephyr base, so that's what I'm doing. Next is defining our project name using the project command. So do project data proj is what I'm going to call it. There's more that you can define here in this command, but for our purposes I think this is enough. Okay, almost done. Next is the target underscore sources app private application / main.c command. With this CMake command, we're telling it to add the source file located at applications / main.c to the target that we're naming app. So the app target is predefined by Zephyr as the main application target. So this command ensures that main.c is included in the build for the app target. And I didn't create the main.c source file yet, so I'll do that real quick. And finally, we've got the target include directories command. So this line of code here basically says when compiling the app target, look for the header files that I'm including in app in this directory. And every time we create a service that our target will use, we'll add that path to this command, which you'll see in other videos. So this should be everything we need for now for what we're going to be building out in this video. If not, we'll find out later on when we try to build. Let's move on to building our temperature sensor service. But before we can write any code, we need to look at the sensors documentation to understand what the pins are and how they work. And we also need to decide which pins on our microcontroller will support our sensor. So let's start with the thermocouple sensor. Going through the documentation, you can see it gives a basic microcontroller hookup diagram here. But I made this simpler diagram for you. Okay, you can see here it has 3 main pins for communication that connect to our controller: an SO, SCK, and CS pin. On the controller side, we have a MISO, SCK, and SS. And let's just break these down real quick in case you guys have never worked with SPI. So SO stands for slave out, and that's the data line that the temperature sensor is going to transmit its information on. You can see it connects to the MISO pin on the microcontroller. MISO stands for master in, slave out. So interpret that as the pin that the master receives information from the slave on. SCK on the sensor goes to SCK on the microcontroller. SCK stands for serial clock. Understand SPI communication is what we call a synchronous communication protocol, meaning the communication between devices is coordinated by a shared clock signal. We don't have to go into each separate device and set up the clock rate to all be the same. We only set up the clock rate in the microcontroller. Then CS on the temp sensor is connected to SS. CS stands for chip select. In SPI communication, we can have multiple SPI slaves talking to a controller, but only one at a time. So the chip select pin typically gets driven low for the particular slave that we want to talk to. SS stands for slave select, and I think it's pretty self-explanatory. Now that we understand that, we need to figure out which pins on our microcontroller can actually be set up to be used for SPI. For that, we're going to need our reference manual. The reference manual for my STM32 F303 Discovery, that controller is RM0316, and if you're using a different controller than me, it's probably going to be a little different. But what I'm going to do is I'm going to come over here to where I can see the different sections of this manual and find the section for SPI. Now when I scroll down and see this table 170 here, I can see that I have about 4 different SPI ports that I can set up. In this case, I only have one SPI bus that I need to utilize, so I'm just going to set up SPI 1. So now I need to figure out which pins on my microcontroller are used for SPI 1. And I can probably do that here in this reference manual, but I find it easier just to look at the development kit's actual user manual. So I'm going to find the section where it's describing the individual pins and their different possible assignments. Okay, so here I'm seeing PA4 is SPI1's NSS pin. NSS stands for negative slave select. It's just telling us that the operation of this pin is it goes low when selecting the slave, just as we expected. So then I see PA5 is the pin for SPI1's SCK. Looks like PA6 is for SPI1's MISO. PA7 is for SPI1's MOSI. But we aren't going to be connecting anything to MOSI because we're not sending any information to our sensor. MOSI stands for master out, slave in. So again, we're only receiving from the sensor, so we won't connect that up. Okay, now let's connect up the pins for real. You can reference this diagram if you want. It's just too hard to show you with the actual wires. Things are pretty messy, so utilize this diagram to make it a bit easier to understand. So on your controller board, you're going to have a 3-volt pin as well as a ground. The 3-volt pin on your microcontroller needs to go to your VIN on your sensor, and ground goes to ground, obviously. Notice nothing is hooked up to 3VO. That's just another way to pass the 3 volts on to another SPI sensor if we had one. Kind of daisy chain the power down the line. But leave that one alone, unhooked. The MISO pin on our controller is going to be, it's going to go to the DO pin here, which stands for data out. The NSS pin on our controller is going to go to the CS pin on the sensor, and the SCK pin is going to go to the CLK pin on our sensor. And of course, you need your thermocouple wire hooked up as well. Okay, cool. Now that we have that all sorted out, we can actually start writing code. Let's start off by including our TSS header file. And then let's include some things from Zephyr that we'll need. First, we need access to Zephyr's SPI API. Then let's get the device model API, which allows us to do things with the device tree, which we'll touch on briefly here in a minute. And then, of course, let's add the logging API. Don't mind these red squiggly errors. I don't know how to fix this. It's something to do with VS Code not recognizing them. But I want to go ahead and register this device for logging so that I can print out information as needed to the terminal. And we do this with log module register. And with the first argument, the name of the service, TSS, and then the log level, in which our case is debug. Then let's create a couple macros that we'll need. One for getting the SPI1 node defined in the device tree, and another for the SPI bus frequency. Okay, we're going to talk about device tree real quick because it is a major part of Zephyr that you need to understand, at least at a basic level. Device tree is just a structured way to describe the hardware components of a system, such as processors, peripherals, and their configurations, and so on. Each board will have its own device tree file. So Zephyr comes with a ton of already made DT files for various development boards. For the board I'm using, I can find my board's DT file under Zephyr, and then boards, and then ST, then STM32 F3 Disco. The file that we want is the .dts file, which stands for device tree source file. And then you can open it up. You'll see it has all the different peripherals defined and configured. So if you ever need to configure a peripheral differently, you would do it here. So if you remember, we decided to use SPI1 and found the pins for it in the STM manuals and hooked them up. Well, we're going to find that same peripheral in here, SPI1. And here it is. You can see that everything matches up to what we saw, where they have NSS as PA4 and whatnot. This and SPI1, this is what's called a node label. So we're going to use their node label macro to get this information from the device tree. So let's go back to our code where I did DT node label SPI1 is a special magic macro that Zephyr will use to go into that file, find the node label called SPI1 that we just looked at, and then attach that information to our defined macro SPI1 node. I've got bus frequency or clock speed set to 1 megahertz or 1 million hertz. I can't remember why I set it to that, I'm going to be honest. I think 1 megahertz might just be standard speed for SPI. I'm sure you can change it up based on the information from your board's manuals. Here's another reference point for you as well. The sensor speed characteristics here in the MAX 31855's datasheet, it calls out just the max clock speed at 5 megahertz, and we're using 1 megahertz. We need to create a configuration struct for the SPI bus now. Okay, so what is this struct doing? It's configuring a SPI peripheral. Okay, we're defining the behavior of the peripheral. You can see here that we're inputting our SPI bus freq macro for the frequency. For operation, we're saying this controller is the master. The word size is 8 and it's half duplex. Our chip select is null because the microcontroller already has an inner chip select logic and it's going to handle it for us. At least I'm 90% sure on that explanation. So if I've got that wrong, please let me know in the comments. Okay, now we're going to get a reference to the SPI1 device in Zephyr's device tree and assign it to SPI1 dev utilizing that macro that we made earlier. So these two sections of code here, the configuration struct and peripheral reference struct, let's explain them simply. The configuration struct called SPI config, that's a container holding the settings for our SPI peripheral. The SPI1 dev struct is holding the reference to the actual hardware. So when we do things like read data from the sensor with the SPI read function, we'll have to pass both of these structs to use the read function. Okay, now let's create some global functions that our applications can actually use to interact with the sensor. Let's create an init or initialization function that an application will first call to make sure that everything's working as it should. Let's break this function down. So this if statement is simply checking to make sure that the SPI1 dev didn't get set to null when we created the struct earlier up above. Why would it get set to null upon creation? Well, there's a few possibilities. It could be that the SPI1 node is missing or misconfigured in the device true file, or it could be disabled in the device true file. Another reason is that maybe we forgot to enable the SPI1 driver in our proj.conf file, or the less likely reason could be that there is an issue with the SPI hardware itself. Also, I'm sure you notice this global keyword here. I'm just using that to easily identify non-static functions. So this is where our general includes header file comes into play. Let's define global in the general includes header file, and then we'll add that to the header file. We'll add that header file to our TSS header file. Now let's create a function that allows us to read data on the sensor. Okay, let's break it down. I've created a function called TSSRead that has no parameters because all it's going to do is return back the temperature. Then I created an array buffer of type uint8t with a length of 4. This array buffer is going to store the data that we receive from the sensor. And then we have two structs. So the first one here is SPI RxBuff. We need this struct to tell the SPI driver where to store the incoming data, which is the buffer we created up above, and to tell it how much space that we've allocated in the buffer. Then we have SPI RxBuffer set. It's sort of a weird one in our case, since we only need one buffer, but the SPI driver requires it. It's a struct to tell the driver which buffers are to be used and how many there are. So technically we could have multiple buffers here, but again, we only need one. Then we've got the SPI read function. This goes back to what I was talking about before. To use SPI read, we have to pass in the reference to the SPI1 device that we gathered from our device tree. We have to pass in our SPI device's configuration, that struct that we created earlier up above, and then of course the set of buffers, in our case just one buffer, so it knows where to place the read data. Okay, cool. So we got our read function, but the problem is this isn't good enough, right? All this function will do is read the entire data message. And the problem with that is that the sensor is sending more than just temperature to us. It's actually sending quite a few different things. So if we look at the temperature sensors data sheet, the MAX 31855. If you go to table 2, it looks like in the memory map, you can see here it details everything that it sends to you. So if you look here, bit 0, if that was high, if that was a 1, that would indicate that there was an open circuit on the sensor. Bit 2 shows if it was a 1, there would be a short to VCC. You can see here that there's some bits that don't tell us anything, they're reserved. It gives you the internal temperature data of the sensor. Probably, I'm guessing that's its reference. And then, I mean, it's got a fault bit, right? So all this stuff is great, right? If we were making and designing a robust application that was going to be, I don't know, in a product that was being sold or deployed to the field, we would want all this information. We would want to know if there was a fault. We would want to know if there was a short to ground on our sensor, right? But in our case, we don't care. All we care about is this portion of the message, which is the thermocouple temperature data. And you can see here that portion of the message ranges from bit 31 to bit 18. So let's break this down so we get a better idea of what's going on here. So I think right now one important thing is that, okay, how many bits are there total in this message, right? So there's 0 through 31, which means there's 32. Let's see if I can get my pen to work. Okay, there we go. 32 total bits in this message. All right. And we created an array, our buffer array. Let's go back to it. Remember this guy right here. This is the buffer array that's going to store that message. It's a UINT8T, and our buffer length is equal to 4. So, okay, that means we're going to need 4 different indexes in our array, because each one is 8 bits long, right? So let's draw it out here. So there's 1, 2, and then we don't really care about 3 and 4, but we have, this is going to be byte 1, byte 2, byte 3, byte 4 of this message that we're going to get. Or sorry, this is actually of our buffer that the message gets put into. Okay, so before we map out, how the bits get put into the buffer, I want you to take a note here of bit 31. This is the sign bit. So what that means is if bit 31 is equal to a 0, that means our temperature value is positive. Okay, if bit 31 is equal to a 1, that means our temperature value is negative. Okay, so I don't exactly know why the message gets put into the buffer the way it does, but I know what happens. So let's just break down how the bits get arranged when they're placed into the buffer. So let's say bit 31 is a 0. It's a positive temperature value. That bit gets placed into bit 8 of byte 1. So there's a 0 there, okay? And so that's bit 31, and then it continues with the same descending order here. This would be bit 30, and we'll just make up some values here. So that's 1, 2, 3, 4, 1, 2, 3. Then we'll say that bit is a 1, right? So this bit 31. That means this bit is 30, 29, 28, 27, 26, 25. This one is bit 24. Okay. So now let's continue on. Let's go to byte 2 here, and it just follows the same pattern, right? So let's make up some values here. 1 0 0 1 1 0 0 1. Okay, so it's the same deal, right? This was bit 24, so now this one is bit 23. Then it goes 22, 21, 20, 19, 18, 17, 16. So this is bit 16. This is bit 17. Now I don't know if you notice, but we need both of these bytes here to convert or to get our temperature conversion. However, bits 16 and 17 are a part of byte 2, and if you look at here, bit 17 is a reserve bit and bit 16 is the fault bit, which we don't care about, we don't want. So in our function we're going to have to drop those off so that we can get the correct temperature conversion. So after we do that, we'll have to concatenate these 2 bytes so that they are in the correct order. And then also another point here too is like when you see bit 18, the least significant bit, it's not 2, it's 2 to the negative 2 power, which was what allows us to get to that 2 decimal precision there. But that's a little bit different as well. So why don't we just like break this down real quick for this function that we're going to create. So let's say we have okay, let's say we get a value in and our byte 1 is 0 0 0 0 0 0 0 1 and byte 2 is 1 0 0 1 1 0 0 1. Okay, so first thing I think we want to do is check to make sure, we want to check the signage of that bit 31, right, which is right here. So we can say, you know, write some code that says if bit 31 is equal to 1, we can set a variable. I don't know, we'll just say sign val is equal to 1. We can keep track of it. Then we don't really want this to mess with our conversion, so what we'll do is we'll actually drop that off. So we'll say bit 31 is equal to 0, since we're going to keep track of it with that right there, right? Okay, and then, by the way, I apologize. Maybe the way I'm describing this pseudocode isn't really helpful, but we'll write the code out here in a second. So then, once we do that, then we want to concatenate. Actually, I don't want to erase all that. We want to concatenate these 2 bytes. So what we're going to want to do is take this byte here and move it over here. And then we'll take this byte here and we'll put it together and make this here. And then 1 0 0 1. Okay, cool. So then we've arranged our bit order correctly. And then what are we going to want to do? We want to drop off these here, right? Because that's bit 16 and 17. And I think that's the fault bit and that's a reserved bit. And we don't want that. So what we'll do is we will bit shift right 2, and that will drop these off. So now we'll just pretend, right? And so if this is a 16-bit value, then it becomes that, right? So now those numbers aren't affecting us anymore, and now we've got the full temperature data, right? So now what we'd want to do is take this result and we'd want to divide it by 4, because again the least significant bit is 2 to the negative 2 power. So this actually ends up giving us degrees Celsius. So then I want this to be printed out in Fahrenheit. I'm American, I understand that a little bit better. So then we can take that value and multiply it by 1.8 and then add 32, and that will give us degrees Fahrenheit. And then, yeah, then we can do something with that. Okay, so let's create another function that processes the data. And you can see here, I already named it right here, TSS, process temperature data. I just haven't created it yet. You can see here that we're passing in this buffer here that data is going to be pushed or placed into. So let's go ahead and create this function right here up above. We're going to make it a static function that can only be accessed by this file. So we'll go, let's see, static. It's going to return back to a double, and it's called process.
Sorry, I don't understand.
Whoops. Okay, that's crazy. Process temp data, uint 8 T, and it accepts in that, we'll just call it data. Okay, so there's our function name. All right. So based on like what we just went over with that pseudocode, we wanted a variable that can track whether it was a signed value or not. So we'll have a bool signed val. I have another one, a double. This is what we'll return back, temperature. Then we had another variable that we'll probably need, uint16t. This is the concatenated result when we put the 2 bytes together. And then we also, I feel like this isn't the best way to do it. Well, this is a uint. Okay. This probably isn't the best way to do this, but it's late and we're just going to cheat. So we will create a couple variables that hold, let's see, is equal to data, a couple values that will hold those first 2 bytes. Again, I don't really like this, but I don't really want to think too hard right now. Okay, so what did we talk about before? First thing we want to do is determine whether the value is signed or not. So we'll just write that comment here. Determine whether value is signed or not. Okay, how are we going to do that? Well, we'll say signed val is equal to temp data 1, and we'll AND it with 0x80, and then we'll say we're just doing a check here, a Boolean check. It's not equal 0. So 0x. So we're ANDing it with 0x80. So let's look at that number real quick. So the hex value 80 is equal to this, right? So if we AND it, we're only considering this final bit here, which is going to allow us to only look at bit 31. Every other value is just going to be 0. So that's that. Let's go here. Okay, so now what we can do is say if signed, goodness gracious, signed val. So if it's true, then I want to get rid of that value. So temp data 1 is equal to temp data 1 ANDed with 0x7f. Okay. So what does this look like? Okay, so 0x7f. So let's go 7f. Okay, so that means we'll keep all the current values in that first byte, but we won't keep that 31st value, that signed value. So if it is a 1, it'll be ANDed with 0, and that will give us a 0. All right, cool. So now we want to concatenate those 2 bytes. We want to put them together. Concatenate the first 2 bytes together. Goodness. And then bit shift right twice. Okay. So then we're going to take that concat value or variable that we created, concat result is equal to, we can say temp data 1, and we want to bit shift that left 8 places so that it creates, well, first we need to cast it to a uint16t. So we create a uint16t, or we cast temp data 1 to a uint16t, and then we bit shift it left over 8 places. Then we OR that value with temp data 2, the second byte, and then once that's done, we'll bit shift over everything to the right 2 places. So I feel like I need to explain this. It's fairly simple, but let's just break down what we did there. So all we're doing is, hold on. Okay. All we're doing is we're saying, okay, I have, I guess I've got, 0, 0, 0, 0, 0, 0, 0, 1. Okay, so that's byte 1. And I want to bit shift it left 8. Well, no, first we are converting it, we're casting it to a 16-bit value. So that actually ends up giving us 1, 2, 3, 4, 1, 2, 3, 4. Okay, so now we casted that 8-bit value to a 16-bit value, a uint16t. Then we bit shift left everything over 8 places. So this 1, all of this here gets moved over 8 places. That ends up becoming 1, 2, 3, 4, 1, 2, 3, 4, and then 1, 2, 3, 4, 1, 2, 3, 4. Okay, so now we have a new value that looks like this. Then we're going to OR that with our first byte, which 0, 0, 1, 1, 0, 0, 1. Okay, so now we're ORing it. So 0 and 1 ORed together is a 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0. Okay, so that should be correct. So now we've got this new value here that we're working with, this one. Now we want to get rid of that fault bit and that reserve bit, bits 16 and 17, I believe, which we still have them, right? They're still here. We haven't gotten rid of them yet. So now we got to take this value and bit shift it right 2 places to knock these off. So now we have a value of 0, 1, 1. Oops, oh my goodness. Okay, let's try this again. Because remember, those go away, right? So now our new value is 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0. So our new value is this, and this actually ends up being our value that we want. So let's go back into here. So now that's what we've done in that line of code. Then we can do, let's see, we want to divide the result by 4 because that least significant bit is 2 to the negative 2. So if we go, we'll just write our comment here, divide result by 4 because the LSB is 2 to the negative 2 to get degrees Celsius. Okay, so now we have our temperature value. We can say temperature is equal to, I'm going to cast it to a double here, concat result, and then we divide by 4. Okay, so that's our Celsius value, but now I want to convert to Fahrenheit. So we can say temperature is equal to temperature times 1.8, and then, come on, we will add 32. Okay, and that gives us our Fahrenheit value. Okay, and then also, obviously, we need to return this temperature value. Sick. All right, so that should work. So that gets returned, and then this returned. Okay. All right. We are not out of the water yet. Okay, I think we've got a service that's going to work, but we still need to do some things here. I think let's go into our general includes, and we're definitely going to need a couple libraries here. Let's see, include standard int .h, include standard defines .h. Okay, that'll prevent some errors from popping up. For some reason this got erased. Let me just copy and paste. Okay. Yeah, I don't know if we put these in yet, but go ahead and put these in here so that these can be accessed by the other modules, such as like our applications or main.c that we're going to do here in a second. What else do we need to do? Our services folder is missing a CMake. So if we come in here and go on the services folder, go do new file, CMake. Okay, you did not end up where I wanted you to end up. What is happening? New file. Here we go. Okay, so every directory in the C project is going to need to have a CMake list.txt file, because when this guy runs this top level one, it's going to go look for another CMake file to tell it where to go when it gets to services. If you don't have this one here, and it needs to be, you need to do add subdirectory TSS temperature sensor service. Okay, that's all that needs to go in this one for it to get to this directory. We did not fill this one out yet, so let's fill this one out. Okay, pretty simple. It just needs to be Zephyr library named. We'll give the library name TSS. Okay, then we do Zephyr library sources. Okay, and we're just going to tell it what the source file is for this library, which is TSS temperature sensor service.c. So TSS. Oops. Service.c. Okay, and then we need to tell it which include files that we want, or where to find the include files. So directories. Okay, so it's called TSS. It's public, and we'll use our fancy CMake current list dir variable. Current list dir, right? So we don't need to add any more onto this path right here. It's just in this directory because look, CMake file is here, and here's the header file. So it's in the same directory. Our module.yaml. Guys, I'm going to be honest with you, I don't even know what the module.yaml file is for, but I'll just put in build, tab it, and then do CMake dot. Okay. I think we're getting really, really close. Hopefully this video isn't like brutally boring, but okay, so we need to rename that. Oh dear God. Can I control Z that? Yes, I can. Okay, we need to rename this to prj, proj.conf, not proj. Here's another one that I added in here because logging by default, it doesn't support floating point. So I'm not sure. I think it would, maybe it would still work with doubles, but regardless, I added that there. You can too. You can not use it and see if it still works. Let me know what happens. Okay. Let's go into main.c now. And we will actually utilize our service. And we're not going to do this in main.c. This is just a test. We just want to see if our sensor works. Okay. The service, the application that we'll create in maybe a couple more videos, I think it's called the CDA, that will be utilizing these functions. But we're just going to test and see if we can actually read something from our sensor. So let's include the TSS temperature sensor service.h, because that will give us access to those functions. Let's include the Zephyr kernel, Zephyr/kernel.h. Okay. Then let's include the logging, Zephyr/logging/log.h. Okay, let's register main.c with logging so we can print some stuff out to the terminal. We'll call it main app and log level debug. Okay, then we obviously need our main function here. Okay, so remember here we have access to the init, and then we have TSS read. So let's go ahead and initialize the TSS service. So we'll say if go TSS init is not equal 0. I don't know, we'll just return -1. And then here's our while loop here. So while 1, we'll go ahead and say log inf. And we'll say temperature, speed stream temperature, %d, or actually, no, sorry, %dot. We'll give it 2 decimal place, %.2f, and then we want to call the TSS read function. And then we don't want this to be going super crazy, so we'll go km sleep, and so we'll sleep for 2 seconds. And then return 0. Okay. I think this should work. So let's just try building it and see what sort of crazy errors we get here. Activate our virtual environment because it wasn't activated. Okay, then we will build it. Well, didn't take too long, but I guess while it's building, I don't know if I already explained this yet. When we built the Blinky sample, we gave it a path, right? It was like Zephyr/sample/Blinky or something after the board. We don't have to do that because our CMake build file is in the same directory, or is on the top level directory. So don't be confused by that. Let's see, what do we got going on here? Okay. Let's see what happened. No sources given. I don't think I've ever even seen this issue before. It's probably really stupid and easy, but okay, wait. CMake error. Okay, I'm blind. Services, TSS, temperature sensor service. CMake, okay. Target include directories. Call with invalid arguments. I did not see that. Okay. called with target include directories called with invalid arguments. What did I CMake current list dir. Okay. Public is supposed to be all caps. Alright, let's just start with a fresh build here. So delete the build folder. Let's build it again. Oh, it's screwed up again. Okay, so board is not being defined on the CMake command line. I don't think that's an issue. Configuring, okay, command. Oh. Okay, I shouldn't have been reading this. I should have been looking at my terminal. Oh, my Atlanta. Expected identifier before dot token. Okay, so I know that is in our... Where are you? Let's see, dot .cs. Okay, so dot .cs was up here. Okay, so I have a period there. Let's try building again. Okay, so we have one warning. I'm not able to figure out what that issue is, but everything built successfully. So I've got my board hooked up. I'm going to go ahead and do west flash it to the board, and then we will use our serial monitor to okay, so it's done. So the successful flash, serial monitor, come in here, COM3, that's where my board is hooked up to. Baud rate's at 115/200, so start monitoring. Boom! Look at that, dude. Okay, so I'm going to put my fingers on it. Let's see, look at that, it starts heating up to 91, 93. Okay, that's epic. It's working. So, congrats. You made it this far. That was brutal. I mean, that was a brutal video. All that CMake and device tree, and then, oh my God. Okay. Well, next video, what we'll do is we will work on the RS-485 part where we're reading in data from a a device. So yeah, thanks guys. If you made it this far, appreciate you, and have a good one.